So we move to our last section, which is waves. Okay, and so we start with a system which we already used to. So this will be a system with masses and springs. And you can think of it as kind of toy model for one-dimensional crystal. So what the system is that we have equal masses connected by springs. And so on. So the masses are all the same. And springs are all the same, so they have this coefficient k. And you can think of it as particles with interacting elastically with each other, and they can vibrate. So they also distance is the same. So the distance between all of them is the same number L. So we already saw this system in several versions. So when you have just one mass, it's a harmonic oscillator. Then we studied the two-mass system at some class of oscillations of conservative systems. Then three masses, you had it as a home exercise. And as you get more and more masses, it's becoming more difficult to solve. At the same time, if you take infinite number of masses, it becomes again solvable. So we consider infinite number of masses. So we can number them. So we can consider positions at rest. So if the system does not move, the position of rest will be x. I use which index n. Un equal ln. So n is an integer number, L is a distance. So at rest, they are at position xn. And then if they start moving, so we will define the motion relative to rest by the variable un. Un plus 1, and so on. So un minus 1. So u will be the position relative to the rest, to the equilibrium, is given by un. So un is some number, real number, so which is given for each mass. So un is how much the mass is moved to one side or another relative to the equilibrium. And then we can write equations of motion. So equation of motion we can write. So we write Lagrangian function. Lagrangian function is kinetic energy, so 1/2 sum over all masses. Well, we can put m also outside, and then velocity squared. Right. So this is kinetic energy, and then minus potential energy. Minus potential energy comes from each pair of this. Of the springs, so it's also n, and then with so elastic energy from a Hooke's law, remember k over 2 with this coefficient, and then we should sum the spring, the size, the extension of this of each spring. So extension of the spring is difference between left end position minus right end position squared. Right? So this is Lagrangian function. Okay, so now we find equation of motion. So equation of motion, the Euler-Lagrange equation. So what we do is usually it's time derivative with respect to the partial derivative with respect to velocity minus partial derivative with respect to position equals 0 for on all n. So we will have infinite number of equations. So the first term, we know what it is always mass by acceleration. And now we have to find the next term. So the minus with minus give you plus. And then you should find where the un enters. So un enters in two terms here, right? It enters in the term un minus 1 squared and un plus 1 minus un squared. So whenever you have mass un, it enters into the potential energy of the right spring and left spring. So there are two terms. So from the first term you get k un minus 1. And from the next term you will get minus. It will be minus k un plus 1 minus un equals 0. So that's equation of motion. Now we can just put everything in. What we'll do? Divide by m, right? Divide by m and put everything inside. So it will be un double dot plus k divided by m. And then what will be inside? You see there will be twice un minus un plus 1. Yeah. Let's write minus. Put minus and then I'll do the way around. So we'll start with un plus 1. Then un minus 1 minus 2un equals 0. So that's equation of motion that we have. So now the next step, what we do is you probably saw this system of that kind when you have a very long spring, and of course it has its own mass. So you can think of a long spring as masses with springs in between as a model. And you remember that if you push it, you have some waves going left and right. So we have to get somehow the waves coming out of this equation. And the way to see the waves is that you will see the waves if the motion. So what was this? Well, so if the displacement of all the masses change slowly, yeah. So if this mass displacement is more or less the same as this mass displacement, is more or less the same as this mass displacement, and so on, but it changes slowly along. So this is a wave. So you have a displacement slowly changing along the system. So we have a slow dependence on n. And slow dependence on n, what it means that if you plot un as a function of mass, so you have like this mass, the first mass displaced on certain amount, another in certain other amount, and so on. So this is how you can see the slow change of displacement. Means that they kind of lie on the same, on a smooth curve. Right? So there are no abrupt changes. So slow dependence on n means that un can be as function of time, can be approximated by some function, which now computed at the position where the smooth function computed at the position where the mass is at rest and at time. So where u of xt is a smooth function. So that's what means that there is a slow change, slow and gradual change of the deviations of all masses along the system. So they can be approximated by the smooth function. And if it's approximated by smooth function, we can try to compute this term by Taylor expansion. So use Taylor expansion at x equal xn, and then we also use at x equal xn, right? So if we use Taylor expansion at x equal xn, so what we have? So so essentially what we need to find is un plus 1, un plus 2. So un plus 1 so let's not write the time. So un plus 1, which is u at position x n plus 1 and t. Okay, I'll keep t. Then we can write it as u x n plus l t. And then we expand it in L. So this will be u at x n t plus du dx L, right? The first derivative, then the second derivative. That's 1/2. Also all at the same point. And then higher order terms. So this is un plus 1, and the same way we can find un n minus 1. So this will be u at xn minus l t. Because this is what is xn minus 1 is. And then it's the same expansion, but with different signs. So it will be u xn t minus du dx, computed at xn l plus 1/2 d2u dx square n l cube l square plus cubic term. Next term is expansion. So now we put this all to the equation of motion, and we find that un d second derivative. So also let's remember that un of t is u at x and t. So it means that double derivative is just second partial derivative at point xn, right? And then we put everything in the equation. So you get second derivative of u minus k over m. And then what you put here inside is, so let's put it in. So we put this piece. So this piece, so we start with that, right? So this is un, right? So it will be un plus du dx plus 1/2 d2u dx2 I will put this term at the end. So then this is also un with minus. Like this, equals 0. And and minus, we forgot minus 2un. So what you can see is that 2un cancel with this un and this un. Then we also cancel derivatives, first derivatives. At the end, what you get is d2u dt squared at the point of the mass or the rest of the mass minus k, and then it will be L squared over m. 1/2 will cancel because there's two equal terms. There will be second derivative with respect to u, x plus higher order terms. So next we do the two things. So we consider for small L. So if we now consider that the distance between masses is short, which is the same as saying that the change is very slow. So for small L, we neglect this small term, which is the next order for the slowly changing function. So we can neglect this term. And then we also consider, we introduce the number a such that as a squared is this value. And this value, actually, you can see what it is. Let's put one L below. So it will be KL divided over M over L. And this you can see what it means. This, when you multiply the spring constant by length, what you may remember from the school course of mechanics, that this will become a spring. So constant, elastic is a constant of spring of length 1. So this is kind of normalized spring constant. And mass divided by length, it will be a density per unit length. So how much m divided by L is what is the mass? So how many masses? 1 over L is how many masses are on a unit length. So m divided by L is a mass on the unit length of the system. So this is a definition. So we will call it sound speed. In general, but it's not necessarily related to sound, but let's just use this name. So then what we do, since the points are close by, we forget that this equation is only valid at points xn, and assume that it's valid everywhere. So then we finally obtain the equation, which is for that function u, which approximates positions of all masses. In that form, and this is what's called wave equation. So that's what the equation which will give us the waves. Which we'll see just slightly later. So what I want to do, so first notice is that we found this equation from kind of toy system of masses and springs, but somehow this type of equation appears for different A's. So it appears in many different systems, like electromagnetic waves, in different type of elastic waves on the surface of water, and all kind of waves. This equation you may encounter. So somehow this equation is universal. It's universal in the sense that it appears in completely different type of physics, and in principle, every field or where it appears, you can derive it in somewhat similar way. But since it's universal, there should be different derivations. So we will consider different derivation, which is kind of shows that this equation naturally appears irrespective of the physical nature of the problem. It just appears from some symmetry considerations. So just like we used symmetry before for one reason, so we will see that a wave equation can come from symmetries, not only symmetries and some very general qualitative assumptions. So let's try to make this derivation. This derivation is not that rigorous, but it gives you understanding why it appears everywhere. So wave equation. So what we will do, we will consider several assumptions. So we will consider we will consider a system which is a system is in one-dimensional space. So we will consider, for now, we consider one-dimensional space only and time. Later, we will go to higher dimensions. So space and time, and we assume that the system is described by the state, which is a function. So it's a function given, which is a real number, and it's given at every position every time, right? So for example, for our springs and masses, it was the displacement of the mass. For oscillations of a chord, it will be deflection from a mean position. For the wave in the water, it will be height, and so on, right? So for electromagnetic wave, it will be like electrical field. So we have one function, and we assume that it's just number, so it's scalar, it's not vector, for simplicity. So we have this system. So what we will assume. So it put some. Actually, I made it with 6 hypotheses. So the first hypothesis is that the uxt is if it's constant, is an equilibrium for any u0. So constant solution is always in equilibrium. So it is nothing. So in a sense that if the only motion is when the state is changing in x. So if u does not change in x, it will not change in time. So that's kind of logical. For our springs and masses, it's also true because constant u means that all masses just move to the same position. If you move all masses, springs will not have any extension, so they will remain in equilibrium. Good. So the second hypothesis is that we will consider small oscillations near the equilibrium 0. So we will assume that we took a system at the equilibrium where everything is 0 and just consider small oscillations. So not something very violent, so something very mild. Then H3, the third hypothesis is a system. The system is homogeneous. This is very familiar hypothesis. Homogeneous both in space and time. So nothing. So at every position and every time, the properties of the system are the same. Then there are 2 hypotheses that we never used, but they were a part of the symmetry groups that we considered from the very beginning. So one hypothesis is parity symmetry. Parity is when you change x to minus x. So you reflect the axis. Essentially, this is when in 3 dimensions, it's when you reflect the left hand to the right hand. And it's assumed that this is the symmetry of the system, so system will not change. And the next is the same with respect to time, so it's time reversal. Time reversal symmetry. So we will consider the symmetry which will not change, a system which will not change if you consider time going forward or backward. And this was also the system of property of all Lagrangian systems that we considered from the very beginning. Just we never used this property. So these 2 properties we always had. And then the last one, which is important, is that we consider it's what's called long wave approximation. Long wave approximation means that the oscillations are large scale in space and time. So what this means is that whenever we consider oscillations, they should be very slowly changing in space and very slowly changing in time. Yeah, so that's an approximation that we consider. We will not consider very violent waves. So something which changes very slowly, just like what we did here. So we consider that everything is very slow. Okay, so that's it. So essentially, as you can see, that we had some symmetry or approximation assumptions without even telling what is the physical origin of the system. So it can be even oscillations of prices for the kind of economical system, or oscillations of small oscillations of number of species in nature. So many things can fit into this program. And if they do not fit, we will see what also can be done. So we can, if some of the hypotheses of are broken, we still can get a system. But this will be our start. So we put these 6 hypotheses, and let's see what they give. So consider so we can instead of consider some equation of motion. For u. So consider that there is equation of motion, which there is some equation which defines this function u. So that equation, so how we represent this equation? We can consider, instead of u, we can consider its Taylor series. So the function can be approximated by its Taylor series. And actually, this relation becomes exact if the function is analytic. But anyway, locally it can be approximated. So it can be approximated by its value, its derivative, first time derivative, second time derivatives, third time derivatives, and so on. So at some given point. So if you take derivative of some all derivatives of the function at some given point, this collection of numbers approximates this function very well locally. So instead of finding equation of motion for this function, we will find equation that relates derivatives. So in other words, we are looking for some function of this derivatives, which is equal to 0. So this will be our equation. So every equation, if there's a equation, you can put everything to the left-hand side, write equal to 0. So in principle, this equation may also, we took this equation at point x and t. So it means that this equation can also depend on x and t. At the point where we computed all the derivatives. So then the first hypothesis tells you that equation of motion, no, not the first. Third, right? H3. H3 tells you that the equation of system is homogeneous in space and time. So whatever equation you write, it will be the same at every point. So it means that f does not depend on x and time. So there is no, we kill this dependence. So the next hypothesis we use is that we consider small oscillations. We consider small oscillations, which mean that all of them are small. All of them are small. That gives us. Then we can use a tool that we already many times use. If the variables are small, we can consider linearization. So we can linearize f at 0. So near u equals 0 and all derivatives to be 0, right? So near all of them to be 0. And if you linearize, what you get is a linear combination, as always. So if you linearize with respect to variables, the result is linear combination. So instead of this function, we get, so how we write? So we write C00U plus C10 du dt plus C01 du dx plus C20 d2u d2 squared plus C11 u dt dx, so on equals 0. So you already see that I coded by indices how you take derivatives. So if there's 2, 0, it means second derivative with respect to time, no derivative with respect to x. And here 1, 1, it's first derivative with respect to x and first order with respect to t and x. And that there is no free coefficient, because if there is no free coefficient, because when everything is 0, it should be 0. So there's no free coefficient. So let's actually write it. So plus c. So in principle, this is a linearization, but from first hypothesis with u0 equals 0, we know that if you put u0 equals 0, that means that all derivatives are 0, including u, then c is 0. And then we use the same hypothesis with u0 not 0, but all derivatives vanish. Then all these derivatives, all these terms become 0, so you will be only left with that one, which should be 0. So you will be left with C00 U0 equals 0. And that means that C00 is 0. Right? So we already we removed these two terms. Okay, already better. I forgot the hypothesis. No. I forgot to write that it's stable in a sense that we will understand later. Equilibrium should be stable, because if equilibrium is not stable, we will not see it, because it will just be broken very soon, which is also a case in some systems, but we will not be interested in unstable situations, so only stable. Okay, so we removed two coefficients, and now let's see that we can remove many more coefficients. Actually, what we can use this. First, we can use parity, which is H4, which means that if you change x to minus x, nothing should change. But whenever you change x to minus x, what will happen is that all odd order derivatives with respect to x change sign. Okay, so if you change x to minus x, derivative du dx will change sign, and this derivative with respect to 1x will change sign. And only the second order derivative will not change sign, and the derivatives when there is. So only even order derivatives will stay, and odd order will change sign. So that means that if we want to have equation of motion invariant with respect to change of x, this term should not appear. So no terms with odd order derivatives with respect to x. And now exactly the same argument works for time. So if we change time, change sign of the time, then all odd order derivatives, first order, third order, fifth order derivatives will change sign, and this term should not be here because otherwise it's not time reversible equation. So also no terms with odd order derivative with respect to t. So it's already much simpler system. So it means that this term cannot appear. There is first order derivative with respect to time. This cannot appear first with respect to x. Here first time and first x, so it's certainly cannot appear. So we removed many terms. So what is left is C20 second derivative, right? Oh, with respect to time, plus C02 second derivative with respect to x. Then it will be C40 fourth derivative plus C22 and plus C04. Etc. So this equation, so where only even order derivatives are present. But still, the equation is complicated because there are many terms. So to decrease the number of terms even further, we will use the last equation, which is long wave approximation. So long wave approximation means what? Means that the function change. It means that for example, for long wave in x direction means that u will change slowly. It means that it will change only at large distance L, right? So the change which you will you will see a considerable change of the function will only happen at L, which is large. Right? And the same if, so that's for given, for u xt for given time. And the same if you consider u as a function of time at fixed x. It also will be something like this. So it only changes at t capital time, which is also large. So you need to look at the long distances to see any change of your variable. And also you need to, if you sit in the same place, you need to wait a long time in order to see any change. So what does it mean analytically? It means that our function u xt can be written as so let's change variables. So let's change variables. So we can change variables. We can use change of variables where we consider psi to be x divided by L and tau consider t divided by t capital. And if you can change these variables, you define u capital of xi tau to be small u of x and t, right? So x and t, which is same as small u at L xi t capital tau. So what you gain by this change of variables? What you gain by this change of variables? Now u change at characteristic scales, which is 1. So in order to see large change of u, it's enough to change psi by 1 more or less and tau by 1 more or less, which means that all derivatives, so m plus n, right? So all derivatives, so we have derivatives odd, so all derivatives to m plus to n they're all of order 1. So all derivatives for all m and n. So the function just changes at size at distance 1, means that all derivatives of the function are more or less. So all derivatives of the capital function, u capital function, are more or less of order 1. And then let's see what it gives for these functions. So for these functions, if we compute the same derivative but with respect to original variables, we always started with time, right? So let's start with time. So what you do? Remember this u is the same as u capital, right? But time is t tau. And x is L xi. So each derivative with respect to time is the same as the derivative with respect to tau, but multiplied by t capital. So what it will give, it will give you 1 over t to m, L to n, and then you can write the same derivative in new variables. Like this. This is for the 1. This is scales as 1 over t to m, L to n. So what you see is that in long wave approximation, we consider T and L large. So in mathematical words, they both ascend to infinity asymptotically. So T and L large, which means that the higher order derivative terms are small. So it means that higher order derivative, you put m and n, larger m and n, smaller the derivative, right? Because these t and l are large, they ascend to infinity, so they're in the denominator, so that larger m and n, smaller is this value. So we can, which we can mean that we can neglect terms with higher order derivatives. So in this sum, the higher order derivative is smaller the term. So we can neglect them. So we just keep the lowest order derivative terms with the second order derivative there and second order derivative here. So all of the rest we neglect. Small. So we neglect it. So this is a strong hypothesis of long wave approximation, which just allows us to remove the rest and just keep the smallest order derivative, which is still small terms, but much larger than the others, because this term will decay as a t square or L square, and the others will decay as will be much smaller because the power will be larger. Okay, so then we came out with the equation, which is just these two terms. This is the beginning, so I can remove it. So what left is that just two terms, these two terms, C20, d2u dt squared plus C02 u dx squared equals 0. So now divide everything by this term. So when we divide, we have C02 divided by C20. We don't know if it's positive or negative, but what we say, we take an absolute value and call it a squared. Okay, so we call it a squared. So we don't know the sign, so it's either plus or minus a squared d2u dx squared. So it's almost wave equation, just we need to decide about the sign. So the sign. So so if we take plus sign, so what will happen? So if we take plus sign, so then the equation will be plus. So what we will, you can check is that then we can find a particular solution which has the form u of xt equal exponent akt cosine kx. So it is a solution C. is a solution for any constant C and for any C and K. So you see, whatever K you put here and whatever C you put here is a solution, because second derivative of time with respect to time will give you a squared k squared, right? A will cancel. And second derivative with cosine will give you minus k squared. So k will appear in both sides. Everything cancels and it will be minus. So everything will be canceled. So check, because so when you put it to check it. This is easy. But what this solution is, this solution is small at time t0. So at time t0, what it is? U at x0 is just c. It's just c, right? When you put c cosine kx. So if c is small, so we can choose the prefactor such that this solution as small as you like at initial time. But whatever c you choose, it becomes infinitely large as time goes to infinity. Right? So let's take k positive. So if you take k positive, whatever c small c you take, it exponentially grows with time, so it becomes infinitely large. So you can start with arbitrarily small initial condition and you always become very large at large times. So it means that this situation is unstable. So equilibrium is unstable. So the equilibrium which was 0, where we're nonlinearized, it's unstable because we can we can choose arbitrarily small initial condition, which will become arbitrarily large for large time. So this is unstable, and but we assumed in the first hypothesis that the equilibrium should be stable, which means that the first hypothesis means that we must take minus sign. Right? We have to take minus sign, and this gives us the same wave equation as we had for masses and springs. Same equation, but we never used any physical origin of the problem. We just use this set of hypotheses, so that system does not even have to be a physical. It may be some other. It can be biological, chemical, or sociological, or whatever you like. So whenever you have these conditions satisfied, you get the wave equation approximately. Okay, so let's make a short break. Let's not make it long because we have a lot of things to do. Okay, so coffee. Oh no, tea. continue. So just a small observation is that what happens when you consider x in larger dimension, for example, in 3 dimensions, let's say. Then you can add one more hypothesis. So when you put it in higher dimension, what you get is that you will see that you get the same equation, but now with all kind of you will have coefficients, several unknown coefficients, because you will have second derivative with respect to x1, second derivative with respect to x2, second derivative with respect to x3. So you can add one more hypothesis, which would be 7, is that the system is isotropy. Isotropy in space, which means that the space is the same in all directions. So in that case, what you can derive that I will not do this, but in that case, the wave equation can also be does reduce just to a single constant, and it has this form du dt squared minus a squared Laplace operator u, where Laplace is just notation for the sum of second derivatives with respect to all coordinates in your space. So that's a generalization of the wave equation to higher dimension. So not much things change. So what we see that all these different systems, they depend on so in every situation when you have all the hypotheses satisfied, you end up with a wave equation which depends only on one coefficient a, which is exactly the coefficient which brings you the memory from the real system where you apply this equation. So a is what characterizes your specific system. So we can make some examples. So example actually many, because this is a very typical equation. So it's kind of the most basic equation in the theory of waves. For example, the first equation we can consider string. The string, like for example, of a musical instrument. So what you do, you fix the string between 2 points. You put tension. So some force. And then string oscillates. So the strings oscillation of the strings is defined by the coordinate u. So this is a deviation from a straight position, and it's described also by at the position x. So this is oscillation of a string, and this is oscillation of a string is described by the wave equation. And what is a? In this case, a is the square root of the tension divided by density. So this is tension divided by linear density of the string, so the mass per unit length. So in order to find this equation, you need really the physical model. But in order to write wave equation, we already know it has to be this form. So you only need the equation, real equation of motion to define what is A in this system. Another sound wave. Sound waves is another example. So sound waves is the waves of displacement of air or water or waves of pressure. So for example, in gas or liquid. So the U can be pressure, for example, if you want to have a scalar component. So you can be pressure, or you can be displacement of of gas or liquid particles. So in all cases, you get the wave equation, and then in that system, A is really a sound speed. And in order to compute sound speed for every system, you need equation of motion. So if you need to find what is A is, you need this equation of motion. Then another example is electromagnetic wave. So here, what is U? U is, for example, is a field, electromagnetic field. You describe the field, and then A is a light speed. In that case, A comes from speed of light. And again, in order to understand it, you need to write equation of motion for electromagnetic waves and derive what is A. But the equation will just have the same form. And then what we will use in some of the lectures later is the shallow water waves. So what it is? Shallow water waves is you for example, take a tank with water. This is water. You can consider like river or sea. And then you consider the waves. So you consider the waves which have small amplitude, but also they should be long. So the length of the wave should be much bigger than the depth. So the length, so if L is a length and H is a depth, so the condition for the long wave in shallow water waves, shallow water means that the depth is small, so the depth should be much small. Let's write it in that way. So depth should be much smaller than the length of the wave. So whenever you have this condition, then you satisfy the last hypothesis that waves are long, and in that case you get the first approximation, the wave equation, and A in that case is square root of gravity constant by h. Yeah, so if you want to derive this relation, what is A in this equation, you need to know the equation of fluid dynamics, and you have to solve them in order to derive this equation with A. But if you mathematically, if you don't care about A, then you already know the form of the equation. So you see that universality naturally comes from the analysis, and in the rest of the time, what we will do, we will solve this equation. So that wave equation is a simple equation. It's kind of analog of the harmonic oscillator. So in mechanical system, we had harmonic oscillator which we can solve completely, and the wave analog is this wave equation. So we can solve it as well. So what we will do, we'll first write a D'Alembert solution of wave equation. So we want to solve in one dimension. So how to solve? So the way to solve, one of the ways to solve it, we need to find. So we consider x as a full space. So there is no limits on the left or right, and we will find a general. We want to find a general form of the solution. What is a general solution? So in order to do that, we should make a change of variables. Change of variables, we consider instead of u of xt, we take it as other function, v of psi tau, but not the same type psi tau that we used before. Oh no, psi and eta. But we will use psi to be x minus at and eta to be x plus at. So what does it mean? It means that whenever you have x space-time plane, then psi will be constant at these lines. So this x minus at, which is psi equal x minus at equal constant. So psi will be just measuring the direction transversal to these lines. And then we have also lines in other direction where eta is constant. X plus at equal constant. So these are constant line of x and psi, and this is kind of new coordinate system. So a new coordinate system where instead of horizontal and vertical coordinates, we take coordinates which are diagonal. Yeah, so we can do this. It's totally all right. So now we will write instead of having wave equation in that variables, we will write wave equation for v. So wave equation for the variable v. So instead of for computing wave equation for variable v, we need to compute. Essentially, we need to compute this derivative, the 2-second derivative. What will be a 2-second derivative in terms of v? So second derivative are computed. So first we compute first derivative, and then we compute second derivative. So the first derivatives. Let's do it all on the other side. The first derivative. Du dx, how you compute it in terms of v? So now we take, we consider that v is a function of psi and psi and eta are functions of x and t, right? So we can differentiate u with respect to x, and u has the same value. So we can use this v and take a derivative using the chain rule. So we have to differentiate with respect to psi with respect to x, and then with respect to eta with respect to x. Now these two derivatives are both 1. So we just have that this is d dx psi dv d eta. Then the same way we take derivative with respect to time. With the chain rule. Now the derivative with respect to time is minus a and a. So it will be minus a dx psi plus a d eta. Good. And the next is so now it's more convenient to write this expression as it in this compact form. That putting the derivative kind of outside, and this we can also put it in the compact form, so it will be a d eta minus d xi, just changing in order, v. So what we deduce from here is that if we want to differentiate with respect to x, it's the same as differentiating with respect to xi plus differentiating with respect to eta. And from here, we also get that differentiating with respect to time in original variables is the same as multiply by a and differentiating with respect to eta minus d xi. Right? So this is a relation between derivatives in original and new variables. And this gives you higher order derivative as well. So the second order derivatives, you just can take this expression twice. Well, you can do it directly, but this way is shorter. And second derivative with respect to time will be twice, so a squared. And then this d eta minus d xi squared v. This is v. Good. So we have second derivatives, and now we can substitute them into the wave equation. We take wave equation. So it's this minus a squared z. Minus a squared to 0. So now we open, well, first of all, we can cancel a squared already. And then we can open the square, so it will be second derivative eta squared minus twice second derivative d eta d xi plus second derivative xi squared. Then it will be minus. Now it will be all minuses, right? Equals 0. And most of the terms will cancel. And these terms together will give a minus 4 by this cross double derivative. So at the end, we get that the second derivative with respect to xi and eta, no, eta and xi, it doesn't matter which is what is in order, is 0. So this is a wave equation, new variables. So it has a very compact form. So the second derivative with respect to xi and eta is 0. So this is the second. This equation is equivalent to the wave equation, but written in these new variables. So now we can solve it directly. So how we solve it? You remember that second derivative is that you take first one derivative and then take another derivative. So we just write it as taking eta derivative after taking the xi derivative. And the derivative with respect to xi of any function equals 0 everywhere. It means that this function does not depend on xi, right? Or does not depend on eta. Does not depend on eta. So it means that this function which is inside is arbitrary function of psi. It does not depend on eta, but still it can depend on psi. Arbitrary function. But the next step is it's a derivative with respect to psi, so that we can integrate this expression. We take integral from both sides. Psi. So what you get on the left, you get v psi, right? Because integrating derivative, you get v. Equal, there will be plus constant that we put to the right hand side. It's integral of f psi d psi plus constant. But now this was integral of arbitrary function plus arbitrary constant, so this is still arbitrary plus constant, but this constant is can depend on eta, right? So we just integrate with respect to psi, so whatever left can be dependent on eta. So we call this j of eta arbitrary function, and this is still arbitrary function which depends on psi. So essentially what we found is that if v is a solution, it should have a, so v equal, no, there is no. So if v is a function, that its dependence on variables should be as a sum of arbitrary function of psi plus arbitrary function of eta. So it's a general solution. So in other words, if v is a solution of this function, it must be sum of the two functions which depend only on psi and eta. And obviously, if any function of this form is a solution of this equation, right? Because both terms will, the first term will be cancelled by eta derivative, and second term will be cancelled by psi derivative. So this is general solution. And having general solution for the wave equation in new variables, we can find general solution in original variables. So now remember that psi is x minus at, eta is equal x plus at. So we get the solution v u xt, which is the same as this, as f as x minus at plus g x plus at. So arbitrary solution of the wave equation has this form. So any function f depending on x minus at, and any function g depending on xat, and then you can see what it is. So the solution u equal f x minus at, what it is. If you write u as a function of x, then at time 0 is just f of x at time 0. So at arbitrary larger time, what will happen is that if you put t large, it will be just the same shape but moved forward. Moved forward with the speed a, right? So it moved at the distance at, a times t. So the first solution is just a wave moving with speed a to the right. So the first bit is just wave which doesn't change the shape. Its shape is f, and just moving to the right. And obviously the second part is wave moving to the left. the waves coming. So the second part, if you consider u equal the other function, then you start with some function j. This is at time 0. Right? And then it will just move to the left with the speed a. So at other times it will be bigger 0. So it will just, without change of the shape, it will just move to the left. You can take a look and see this. So this wave moving the left with the same speed a. So that already justifies why we use a as a sound speed or wave speed. So a is so because any solution of wave equation can be decomposed as a sum of two waves. One wave will go with the wave speed to the right, another will go with the wave speed to the left. Okay, so this is a general solution. So now we can write a solution of the Cauchy problem. Cauchy problem is the equation of motion plus initial condition. So how to solve an equation of motion if you have given initial condition. And the initial condition means that initial time, which is we set at t equals 0, we assume that we have initial shape of the wave. So what we will show is that actually because equation of motion of second order in time, we need two initial conditions. We need initial position at initial time, and also we need initial derivative. And the initial derivative will be psi. So assume that u is some function. So it has certain shape at the initial moment, and it has initial velocity at certain moment. Like for the masses, remember this masses strings is first position. We need positions at the initial moment and velocities. So let's see that then the system has a unique solution. So we will show that there exists unique solution of the wave equation with this initial condition. So given initial condition, we will show that there is a unique solution, which shows that this is the right formulation of the Cauchy problem for the wave equation. So how you do this? Well, you just use the fact that general solution we know. So we have to show that there are unique functions f and j which satisfy this initial condition. So what it means that initial position is these two functions taken at t equals 0. So phi of x is just sum of f of x plus j of x. This is first condition, and the second condition we have to take derivative. So psi of x is what? It's derivative of u with respect to time, which is derivative of f with respect to arguments, and then argument with respect to time, the chain rule. So it will be minus a f prime of x, right? So this is this time derivative taken at t equals 0. So derivative of f, we write it as prime. Then derivative with respect to time gives you minus a, and taken at 0 time, so at x. The same with g, so it will just sign will be different. Prime is derivative. Okay, so we have these two conditions. So the next step is the next step okay, so next step we take derivative of the first. So let's call it 1 and let's call it 2. So what we do, we take we will take derivative of the first, so that it will be f prime of x plus j prime of x equal phi prime of x. This is first equation, and the second equation we derive divided by a, so it will be minus f prime of x plus g prime of x equal c of x over a. And then you can solve them. So you see, if you take the first minus the second and divide by 2, g cancels, and you get f prime. Dividing by 2, so it will be the first divided by 2 minus the second divided by 2. So this is how you find f prime, and the same way you find g prime. So you take a sum, divide by 2. Okay, we found primes. So the next step is we can integrate both. We take integral with respect to x, integral with respect to the x. When you integrate, you get integration constant that we will put at the end. But the first gives f, this gives psi, this gives integral of phi integral of psi. So we will integrate, and we will put integration limits clearly from 0 to x. From 0 to x. So then we get that f of x equal psi of x divided by 2 minus 1 of the 2a integral of psi of x dx. And then there will be integration constant that comes from these integrations that we just said C1. We will not look for, we will find it on the next step. And the same for g. When you integrate the second equation, it will be phi of x by 2 plus 1 over 2a integral psi of x dx, and then integration constant. So then let us use equation 1. So equation 1, which is this one. You see, when you sum the f and j, you have to find psi. So we have to take a sum, you get psi. Integrals cancel. So the sum of the coefficients should also cancel. So we already found the relation between integration coefficient, integration constant. That's all what we will need. Because now we can substitute everything to the solution, and now we know that what is the solution. U of x and t are the sum of the functions f and j taken at these limits. So this will be sum of phi's, phi x minus at plus phi x plus at divided by 2. And then there will be sum of the integrals. So it will be plus 1 of the 2a. But look, this integral will come with x plus at. And this integral will come with x minus t and with minus. So when you subtract, it's just the same as putting x minus at below. So you'll see that the sum of these two integrals with plus and minus if you take x plus, no, let's make it, probably this is not very clear. So I'll make an intermediate step. So x minus at plus g x plus at. And then you use these two expressions inside. So the first term will be with psi, with phi. By 2. And then the integrals will together will give you x plus a t will be at the top, and with a minus x, together two integrals will add up to this expression. And some of the constants cancel. So this is the D'Alembert solution. So this is the solution to our initial value problem, because you see, given initial state, initial speed, we find a solution at any time by this formula. So this is D'Alembert solution. So let's write just a simple example of how it works, because this similar solution will be on your home exercise that I'm going to give on Monday. Here. So what we will do, we will consider u at time equals 0. For example, we will consider that initial deformation is like this. So this is our function phi of x. So this is the initial position. So assume that you have a very long string, and then we just took it, deformed it in the middle, but deformed, but without giving any speed. So the speed du dt will be just 0. So psi 0. So we make an initial deformation, but without any initial speed, and leave it. So what will be the solution? So the solution will be is the sum of the two waves divided by 2. So the half of the shape will go to the left, half of the shape will go to the right. So this will split and go in two directions. And let's just see what will be. So this is our original shape. Half of the shape means just divided by 2. So this is phi divided by 2. So as time grows, one half will go to the left. So at later times, one will go to the left on a distance at. Another will go to the right at a distance at. And the solution is the sum of the two. So the solution will be the sum, which is this shape, right? So this is a solution at t. So this is solution at t equals 0, and this is solution at t positive. At later, they will just separate, and one wave of the same shape will go to the left, another the same shape will go to the right. You probably can see that on a string, on a very long string, or on a chord. When you deform and leave, you will see that half of the one piece will go to the left, another piece goes to the right. So this is a wave equation. Or, for example,
in the water, if you make certain deformation of water and leaf, there will be one wave going left, another in a channel. One will go to the left, another goes to the right. So that's wave equation. So if you just put initial deformation, it will split into the two waves. And if you put initial speed, so if you, instead of deforming, you just accelerate, you put some certain initial speed to the wave, it will also be some two waves going two directions. But this way you will make yourself as an exercise. But anyway, given initial deformation, initial speed, we know what is the solution of the wave equation. So that's essentially our starting point of the whole story of the wave equations. And then there will be some complications. So I think that, yeah, we better stop today. So tomorrow we continue with Fourier expansion and spectral method. Okay, so I think we're done for today.